Alrighty, howdy folks. Let's look at the integration by parts. Um, we already learned about the substitution rule for integration, right? So now this is another technique of integrating things. Let me motivate you this way. Motivation. Evaluate integral x e to the x dx, right? So when you see a problem like this, you should be asking yourself, wait a minute, how do I know how to find, what all methods do I know as to how to find an integral, right? The first method you know is what is called the antiderivative. For example, you know that the derivative of sine x is cosine x. So, integral of cosine x would be sine x. Of course, you just add a plus c. You agree with me? You agree with me? Derivative of sine x is cosine x. So integral of cosine x must be sine x plus c. So that's called the antiderivative method of finding the integrals. And similarly, if I say, what is integral of secant square x dx? All you need to say is, wait a minute, what the derivative of what is equal to secant square x? The answer is, the derivative of tangent x is secant square x. So integral of secant square x is tangent x, right? Add a plus c. You're done. And well, while that was okay, for some of the problems like the ones that we saw in 5.5, that didn't work. So we had to learn another technique called the substitution rule. You make a substitution u equals something and then work the problem out. So let's ask, can any of those techniques work to solve this problem? Integral of x e to the x dx. Do we know readily the derivative of something to be equal to x e to the x? Obviously there is something, but do we readily know it? No, we don't. So the antiderivative method of figuring out this integral doesn't work. Let's see, what else? Could we do a u substitution? U equals x. I told you, u equals x is a pathetic substitution. Don't ever do it. Right? I mean, for the u substitution method, u equals x is a bad substitution. Could we do u equals e to the x? Yeah, but that doesn't help much because you end up with integral natural log of x and natural log of u du, and that wouldn't work either, right? So that means there must be some other way that we need to learn to solve integrals, and that's what this integration by parts is. Okay. The antiderivative method this is what I was talking about. And the substitution method would be to plug u equals this, and yep, do either of these methods work for our problem? No. And so what's integration by parts? As simple as this. Integral u dv equals uv minus integral v du. What? Yeah, that's it. Whenever somebody says, hey, what's integration by parts? Oh, you just say integral u dv equals uv minus integral v du. And the proof of it, let me quickly go over it. If you understand it, fine. If you don't understand it, equally fine. Okay, the derivative of f of x times g of x, the product rule we know, is f of x times g prime of x plus g of x times f prime of x. Right? Now, can we solve for this f of x g prime of x by subtracting the other term, g of x minus f prime of x? That's exactly what I did here. And now, if this quantity is equal to this quantity, are we allowed to integrate both sides? Yep, so that's what I'll do in the next step. I'll integrate both sides. But then, am I allowed to split this integral of difference, something minus something? Can I split that into two separate integrals and subtract? formally the way what I'm asking can be put as, is the integral of a difference equal to the difference of the integrals? Integral of something minus something, is that equal to integral of something minus integral of the other thing? Can you do that? Yep, you can. Let me ask you one more. Is the integral of a product equal to product of integrals? That means integral of f of x times g of x dx is integral of f of x times integral of g of x. That's a major no, right? Be very careful about that one. The integral of a sum or difference is equal to sum or difference of the integrals. That's okay, but not product or quotient. Okay, cool. So now, what's this? Okay, we have this. Suppose I were to now make some substitutions. That is, u equals f of x and v equals g of x. Let's also go ahead and figure out the differentials. Do we know what du would be? If u is f of x, du is what? F prime of x dx. Right? Okay, and what is dv? G prime of x dx. Right? So let's write those things also now. And in the next step, let's substitute all these quantities in this integral. That step, that equation that we see there implies, excuse me. Then integral for f of x we plug in u, g prime of x dx will plug in dv, and so u dv, integral u dv, the left hand side. The right hand side is integral ddx of uv, integral ddx of uv. Let me, there's somebody at the door. Let me pause this for a second. All right. Sorry about that. Let's get back to this. Oopsie. Okay, so we make these substitutions, and then what we're going to get is, like I said, the left hand side becomes integral u dv, and this first thing that you see, ignore that for a second. Let's look at this minus part. Would that become v du, integral v du? Yep. But now let's focus on this slightly more interesting one. ddx of uv dx. That's what we end up with. What is that? ddx of uv dx. What does that mean? Integral of the derivative of f function. Right? Integral of the derivative of something, of a function rather. What is that equal to? Well, the integration process cancels out sort of the derivative process, right? So when you take the integral of a derivative of a function, you get the function itself. So basically, the first integral that you see here on the right hand side is actually f of x times g of x. And f of x times g of x is nothing but uv. And that's why we get integral u dv equals uv minus integral v du. Cool? If you understood that, awesome. If you didn't understand it, equally awesome. Just chill. Okay. Next. Let's apply this to quite a few problems, starting with the one that we started off with, which is integral xc to the x dx. We will apply the integration by parts method, that is integral u dv equals uv minus integral v du. Now, what did I say here? Note that we have three options for u and dv. Do you agree with that? let's see what I mean by that. Apparently, the given integral x e to the x dx, we need to look at that as integral u dv. So what is u? Yeah, we have different options. We can say u is x, right? And dv would be the rest of it. What is the rest of it? E to the x dx is the rest of it. So u is x, dv is e to the x dx. That's one option. Second option, u equals e to the x and dv is the rest of it. What is the rest of it? X dx. So u equals e to the x, dv equals x dx. Third option, u equals x e to the x, dv equals dx. Right? And I'm sure you're going, oh, wait a minute, man. There are other options. You could say u equals dx and dv equals x e to the x. And no. The thing is, the dv has to be associated with dx. dv must have dx to go with it. It could simply be dv equals dx. In some cases, that's what happens. Or something like x dx is dv is okay. E to the x dx is dv. That's also okay. So dv has to have a dx with it. Okay, so that limits our choices to 3. So what should we pick? That's the interesting part. So on purpose, I'm going to show you different options. I don't know. Okay, good. Pick one. Let's say u equals x and dv equals e to the x dx. No, I know. When we had u substitution, I said, hey, don't ever pick u equals x. That's a lousy substitution. Is that admonition prudent even in this case? No, it's perfectly all right. With integration by parts, if you say u equals x, that's okay. Whether it's okay for this particular problem or not is something that we'll find out, but as such, u equals x is okay when it comes to integration by parts. Cool? All right. So u equals x, dv equals e to the x dx. Cool. So that's our integral u dv now. To evaluate it, apparently, now let's focus on the right-hand side. You need uv and you also need to integrate v du. Wait a minute. What do we know? Do we know u? Oh yeah, u equals x. That's what we picked. So we know u. We also need v. Do we know v? No, we don't. But what do we know? We know dv equals e to the x dx. Right? When we say dv is e to the x dx, can we figure out v from it? Yeah, we can. Any idea how to do it? If you said just integrate, you are absolutely right. What? How'd you get that, man? As simple as this. How would we have gotten dv in the first place? We must have had a v to begin with, and we must have differentiated that to get dv, right? For example, let's say v equals e to the x. If I said, tell me what is dv? Hang on a second. V would be the derivative of v is derivative of e to the x is e to the x. Dv is e to the x dx, right? So in order to go from v to dv, we would have differentiated. Now to go from dv to v, you just reverse the process, which is you integrate. Cool? So by integrating dv, we get v. So that means we know u, we know v. All we need to do is, we also need a du. Can we figure out du? Yep, we know u to be x, so du is the derivative of x is 1 times dx. So du would be dx. So we know everything on the right hand side. All we need to do is plug in and integrate. So let's go ahead and do that. That's one option. The second option is we can say u equals e to the x and dv is x dx. And the third option is u equals x e to the x and dv equals dx. So those are the three options I was talking about. In fact, let's try the second option first. Okay. Integral x e to the x dx is uv, and the second option says plug u equals e to the x and dv equals x e to. With those things, this is what I typically do. I just write them on the side. I write the original integral on the left hand side and go to the right hand side and write u equals e to the x, dv equals x dx. And then I figure out du. Right under u, I figure out du. Du is the derivative of e to the x is e to the x, so e to the x dx is du. V, integrate x dx, you get x squared over 2. Cool? So that's what I write immediately after I write u and dv. Now, that should equal uv. U times v. U is e to the x. V is x squared over 2. So e to the x times x squared over 2. That takes care of uv. Minus integral v du. V is x squared over 2. Du is e to the x dx. So that's what I write. Right? So, we got this now. uv minus integral v du. Wait, is this good? Why do we apparently use this stupid integration by parts method? Oh, that's because, man, if you're struggling with an integral, like the moment you apply integration by parts, you'll get another integral, but that integral is going to be really simple. Oh yeah, really, yeah? Is integral x square e to the x dx any simpler than integral x e to the x dx? No, if anything, it's more complicated. Yes, what? Yeah, this is a stupid method, man. Dr. Sam, you promised that this would be it. No, it's not, right? Well, don't lose heart though. The reason this ended up being we ended up with a complicated integral is because of our choice of u and dv. Our first choice, that is option 2, somehow didn't help us. So let's try another one. Option 1 as the choice.
Sorry, I'm not
in
sure
this
about
case,
that.
Alexa went nuts. Oh no. So let's try u equals x and dv equals e to the x dx. Now, like I said, immediately figure out du and v. Will you do that? What is du? If u equals x, what is du? dx. If dv is e to the x dx, what is v? Integrate. You get e to the x. Oh, by the way, ignore that integration constant plus c. We don't need that now. We are just interested in the antiderivative. Okay, cool. So v equals e to the x. Aha. So let's do our uv minus integral v du with this option. What do we get? uv. Would you agree? uv would be x times e to the x. U times v, x times e to the x. Minus v du minus integral v du minus integral e to the x dx. That's what we end up with. Aha! As promised, did we end up with a much easier integral now? Yep, integral e to the x dx is something that we know, right? So, x, and what is integral e to the x dx? e to the x. So we have xe to the x minus e to the x. And now at this stage, go ahead and add the integration constant plus c. You must add plus c, right? If in calculus 1, your teacher took off a big chunk of points because you didn't put the darn constant, I'm here to tell you that I wouldn't be any different. You must put plus c. Okay, there's a lot of practical significance to why you need to add a plus c. If you're taking physics, you will find out you're solving some problem like you're given the velocity and you're supposed to find the position. And if you don't know, if you don't add that plus c, then you would be missing out on the adding the initial position in that thing. So there is a lot of practical significance to this. So it is not that somehow math teachers are sadists who just want to take away points from you. Nope, that's not the case here. Okay, all right. Xe to the x minus e to the x plus c. Cool. We solve the integral. So this is the idea behind integration by parts. I'll solve quite a few problems and help you out. Okay. So the question is, man, so you mean to tell me that the whole thing hinges on your choice of u and dv? Yeah, it does. So how are we supposed to do this, man? Do you just do always trial and error? You try one thing, nope, that didn't work. Maybe try another one. Sometimes, yeah, but good news is there is a sort of a rule of thumb that works. For the most part, it works, but don't hold me to it all the time, okay? And that's we use a mnemonic, ILATE. Okay, ILATE is inverse, logarithmic, algebraic, trigonometric, exponential. Okay, and is the way it works is worst choice for dv. The inverse is the worst choice. Exponential is the best choice. Cool. Exponential is the best choice for dv, and things go from bottom to top. As you go, things get worse and worse for dv. Okay, so everything is going to be based on what to choose for dv, and the rest of it would be u. Okay, now let me explain that in terms of our example. Integral x e to the x dx has x in it, which is an algebraic expression. Would you agree? And e to the x is an exponential expression. So, according to this scheme, which one is a better dv? Exponential is a better dv. So that means e to the x dx is a better dv. And automatically, u must be x. The remaining part is u. Right? Always do that. The dv is the exponential part, and that's a better choice. So e to the x dx should be dv, and the rest of it is u. Cool? That's the idea. Now, let's try to figure this out. Now the question becomes, what do we choose for u and what do we choose for dv? Go back to this guy. We have, oh, by the way, we have x and cosine x. X is what kind of an expression? Inverse, logarithmic, algebraic, trigonometric expression. What kind of an expression is x? Algebraic. What is cosine x? Trigonometric. Cool. Which is a better choice for dv among the trigonometric and algebraic? I said bottom to top, right? So trigonometric is a better choice than algebraic. So that means we will make dv to be cosine x dx. And u would be the rest of it, which is x. Right? That's what we see. u equals x, and dv is the trig one, cosine x dx. Cool? And notice one more thing. All of this I did on the side. Cultivate habits like this. And also, as you work on homework problems, be sure to write nicely and legibly. Make it a practice to make everything look nice. Okay, it should look like how my printed stuff is. I have put in a lot of effort into creating a whole bunch of text boxes and all that and arranging them nicely. If and when I write, more or less, it would look exactly like this. Okay, and I implore you, I beg of you, please learn to write well. You're all going to be engineers, and let your work reflect that of an engineer, a future engineer. Okay. One more thing. We live in America where paper is inexpensive, right? So have plenty of paper and be generous. Don't try to squeeze everything into one itty bitty paper page and all that. Just be generous. If a problem takes half a page, so be it. Make it look nice. Okay. All right. So u equals x, dv equals cosine x dx. And what's the next step? Figure out du and v. If u is equal to x, du is dx. If dv is cosine x dx, v is integrate. Now, what's integral of cosine x dx? Integral of cosine x dx. Don't say negative sine x, positive sine x, right? The derivative of cosine x is negative sine x, but integral of cosine x dx is positive sine x. Okay, so that's what we have. And so our integral is solution. Integral x cosine x dx is uv minus integral v du. uv x times sine x minus integral v du sine x dx. And what is integral sine x? Negative cosine x. So x sine x minus negative cosine x, and that's x sine x plus cosine x plus c. Cool? That's the idea. Are you beginning to get a hang of this one? So all this is integration by parts, is uv minus integral v du. Figure out what to make u and what to make dv and use the mnemonic, and you will be in a good shape. Ooh, what's with the 3 stars? 3 stars means that's a very important problem. In any regular class, typically when I give a test, that problem or a problem just like that is almost a guarantee to show up in a quiz or test. Okay, so pay extra special attention to this one, and I'll tell you maybe at the end what makes this problem so special. It kind of looks just like the other ones, man. Yeah, it does, but it's not. Okay, cool. So we are going to use integration by parts for this one. And so what's the deal? What's u and what's dv? Wait a minute. E to the x, what kind? Exponential. Cosine x, what kind? Trigonometric. So which one is a better dv? Exponential is a better dv. So that means e to the x dx. Always associate dv with the dx. So dv is e to the x dx. What is left? Cosine x. So that's going to be your u. Yep. So u equals cosine x and dv is e to the x dx. Right? What's the next step? Du and v. Figure out du and v. Du is what? Integral of the derivative of cosine x is negative sine x. And integral of e to the x dx is e to the x. So we have u, v, solution, I equals, what? I equals? Yeah, there is a reason why for this problem I say I equals, I introduce this, I equals, you will see as to why I did that in just a second. Okay, equals integral e to the x dx, our problem. And that's equal to uv minus integral v du. uv is cosine x times e to the x minus integral v du becomes e to the x cosine x plus integral e to the x sine x dx. What? We started with integral e to the x cosine x dx. Now we end up with integral e to the x sine x dx. Do we know how to figure out integral e to the x sine x dx? No, we don't. What? This... oh, stupid method. Nah, not quite. So what do we do here? Hey, who said we cannot apply integration by parts once again? Right? Guess what? That's what we are going to do. We'll apply integration by parts once again. Again, what do we do? Same idea, exponential and a trig. Cool, we know exactly what to take for u and what to take for dv. Yeah, but because this is the second time we're doing in the same problem, instead of saying u and v, let's call them as u1 and dv1. Okay? So u1 is sine x and dv1 is the exponential e to the x dx. And du1 is cosine x dx and v1 is e to the x. So just for that integral, we'll say e to the x cosine x plus this for the second integral, e to the x sine x, uv minus integral v du, or rather u1 v1 minus integral v1 du1. We'll do that. u1 v1 is e to the x times sine x. Sine x times e to the x. So that's what we see here. Minus integral v1 du1 became e to the x cosine x dx. Cool? So, we did apply integration by parts twice in the same problem. And, what? We ended up with another integral e to the x cosine x dx. Man, what? This is... what do we do now? Hey, apply integration by parts once again, the third time. Yeah, but then you'll get an integral e to the x sine x dx if you did that. Oh, no big deal. Apply again. No, if you did, you'll get integral e to the x cosine x. So you just get into an infinite loop. Right? Man. What do we do? Aha! Check this out. This is why this is a 3-star problem. Not only did we have to apply integration by parts twice in the same problem, but there's something else that we can do now. What are we supposed to originally find? This I. What is I? This particular integral. Right? And we ended up getting another I here. So, could we now just replace this integral with I? What would happen if we do that? We'll get e to the x cosine x plus e to the x sine x minus I. What are we trying to solve for? I. Can we do it? Let me see if I can write. Suppose you have x is equal to, say something like 7 plus 12 minus x. Let me make it 13. 7 plus 13 minus x. And you need to find x. Seven plus 13 minus x, and you need to find x. Is that a big deal? right? Do we have something sort of like this here? You will say, hey, that's piece of cake, man. All I need to do is add x to both sides and I get 2x equals 20 and x equals 10. Right? Isn't that what you would say? Okay. What's stopping you from doing the same thing here? I equals some blah blah minus I. You need to solve for I. So add I to both sides. Right? And you get 2i, I plus I is 2i, and that's equal to this e to the x cosine x plus e to the x sine x. And divide both sides by 2, and you get I equals 1/2 of this quantity, e to the x plus e to the x cosine x plus e to the x sine x, and just go ahead, add a plus c. Cool? That's why this is a very nice problem. It's a classic problem. What do I mean by a classic problem? Anybody, any country, America, Japan, India, China, it doesn't matter. The first time you bump into integration by parts, someone teaches integration by parts, they get to this stage and go, aha, let me work one problem out for you, and they will do one of these problems. Okay, because it's very interesting. Two interesting things happen. You need to first, you're for the first time in your life, you're applying integration by parts twice in the same problem, and then you're also resorting to this I stuff, adding the same quantity and solving algebraically. Right? Cool. Let's move on to the next one. Integral of natural log of x dx. Very interesting one. Up until now, we had something times something dx. But this one is just natural log of x dx. Well, go back to the scheme of things. Natural log of x is what kind of a function? A logarithmic function. That's it. There's nothing else. What kind of is logarithmic function a good dv? No, I late. It's a pretty bad one. It's as bad as the inverse. So you do not want to do you do not want to say dv is natural log of x dx. So for this, it turns out you say u equals natural log of x and dv equals dx. Okay. And then du is 1 over x dx, v is x. Cool. And so we have solution. Integral of natural log of x dx is x uv is natural log of x times x minus integral v du. V is x, du is 1 over x dx. And this reduces to x and x. X divided by x equals 1. And so we have x natural log of x minus integral dx. What is integral dx? What is integral of 1 with respect to x? Just x. So this is x natural log of x minus x plus c. As simple as that. This is one that you may have to memorize. What is integral of natural log of x? X natural log of x minus x plus c. Okay, if you cannot memorize it, no big deal. You can always resort to this integration by parts method and quickly figure it out. Cool. All right. Next, evaluate integral sine inverse of x dx. Again, integration by parts with u equals sine inverse x and dv equals dx. Cool. Derivative of sine inverse of x. You must remember this. That's 1 over square root of 1 minus x squared. So du is 1 over square root of 1 minus x squared dx, and v is equal to x. Cool. uv minus integral v du becomes x sine inverse x minus integral x times 1 over square root of 1 minus x squared dx. And so now the question is, how do we integrate this one? X times 1 over square root of 1 minus x squared dx. All right. Could we use substitution for this? Yep, we did this one back in 5.5. So w equals square root of 1 minus x squared, we say. W square is 1 minus x squared, implies 2w dw is negative 2x dx. And so x dx itself is negative w dw. So plug that in and you would be in business. X sine inverse x minus what did I do? This 1 over square root of 1 minus x squared would be 1 over w, and for x dx I plugged in negative w dw. Are you with me? I'm looking at this integral. 1 over square root of 1 minus x squared becomes 1 over w, and x dx itself becomes negative w dw. That's what I'm plugging in. And so that now becomes integral dw, and integral dw is just w, and replacing w with a square root of 1 minus x squared. Cool? So that's how you do integral sine inverse of x. All right. X to the 5 natural log of x. X to the 5, algebraic, natural log of x, logarithmic. Which one is better? For dv, algebraic is better. So x to the 5 dx is dv, and u is natural log of x. Cool. And du is 1 over x dx, and v is integrate x to the 5, x to the 6 over 6. Right? Cool. And so we are ready to substitute. X to the uv would become uv, natural log of x times x to the 6 over 6. That's what you see here, the first term, minus v du, x to the 6 over 6 times 1 over x dx. We can simplify this, and x to the 6 over x is just x to the 5, and the 1 over 6 is a constant that can be pulled outside of the constant multiple, can be pulled outside of the integral, and we'll do that. And so we end up with 1/6 integral x to the 5 dx. What's integral x to the 5 dx? X to the 6 over 6. So the next step, we'll replace integral x to the 5 dx with the x to the 6 over 6 and simplify this, and we get this. Cool? All right. Integral x squared sine x. This is, there's nothing complicated about it. Algebraic, ilate, trigonometric is a better dv, right? Trigonometric is a better dv, so sine x dx is the dv and u is x squared. And so when we do this, we end up with this integral. Oh, wait a minute. Do we know integral x cosine x dx? No, we don't. So what do? Apply integration by parts once again. As simple as that. So u1 equals x, dv1 equals cosine x dx. The ilate mnemonic still works here. And so when you do that, pretty much you are in business. So we end up with this, and that's all. Okay, just a little tedious. Yep, we need to integrate twice, apply the integration by parts twice, but as such it's not really that complicated. Let's see. Now this is a 5-star problem. I really like this. The thing about this one is it is very similar to that e to the x cosine x dx that we did. What is that? You remember that classic problem that I talked about, e to the x cosine x? This is exactly the same way, but there would be some fractions and all that stuff. So as long as your algebra is good, this problem is straightforward. So let me show you. Again, we'll say I equals for this guy. And I equals integral e to the 2x sine 3x dx. Exponential is a better dv, so dv is e to the 2x dx, so that means u is the rest of it, which is sine of 3x. U is sine of 3x, and I took the derivatives and integrals, and so we have uv minus integral v du. Okay, and we apply that. We have this. Again, notice we ended up with an e to the 2x cosine of 3x in here. So, excuse me, e to the 2x cosine of 3x. So what are we supposed to do? We apply integration by parts once again. u1 is cosine of 3x and dv1 is e to the 2x dx, and figure out du1 and v1. And when you do, be careful about how you write all of this, right? 1/2 e to the 2x sine of 3x, that's what this is, minus 3/2 times, we are applying integration by parts the second time to this integral, right? So that's why I have a minus 3/2, the outside one, and now inside part is the u1 v1 minus integral v1 du1. See, it is this kind of stuff that makes this problem a bit hard. So minus u1 v1, right? u1 v1 is cosine of 3x times 1/2 e to the 2x. So that's what you see here. Minus integral v1 du1. But how come this became, instead of a minus, this is a plus? Yeah, that's because du1 has a minus in it. So minus v1 du1 would be minus integral this one, right? So be careful about that part. And now we notice that this integral e to the 2x sine of 3x dx is I. So we can just write this whole thing as 3/2 I. You see what I mean? So you write this part as 3/2 I. And also make sure, this is where, please pay attention to this. I have noticed that many students miss out on distribution here. You must make sure to distribute this 3/2, minus 3/2, negative 3/2 to both these terms. A lot of times in the next step, people will go, oh, negative 3/2, and that's negative 3/4 e to the 2x cosine x dx. Yep, good. And then just write 3/2 I. No. Negative 3/2 times positive 3/2 is negative 9/4 I, right? So you better be absolutely careful about that one. So minus 9/4 I. Cool. Are we almost done? Yep, all we need to do is solve for I now, like using simple algebra. Add 9/4 I to both sides, and I plus 9/4 I is 13/4 I. 1 plus 9/4 is 13 over 4 I, and that's equal to this stuff on the right hand side. So to solve for I itself, divide by 13/4 on both sides, or multiply by the reciprocal 4/13, and you get 4/13, all of this stuff on the right hand side, and add a plus c at the end. Cool. These are my favorite problems. Every test and quiz that has integration by parts, I will ask one question like this. What I'll do is I may change this e to the 2x to e to some 5x or something like that, and sine of 3x to sine of 7x, or cosine of negative 5x, something like that. So that's what I might do. But One problem like this is a guarantee to show up in a quiz or test. Okay, cool. Hey, that's it. From my side, I have taught you everything in integration